Most of you have probably heard the analogy that open source is free as in puppy. That is, you're responsible for the care and feeding, and it's oftentimes a lot more work than you realize. When you build software using open source libraries, you get the good along with the bad. You get the functionality that you wanted, so you don't have to reinvent the wheel, but then you also get all the vulnerabilities that are inherent in that code base. Today we're going to talk about software composition analysis. Specifically, what does real-world software look like from the perspective of library usage and inherited risk? We'll use data science to uncover some new quantitative insights on how open source libraries impact application risk. And we think you'll be surprised by some of the findings, so I'm going to start with a quick preview. Here are some of the things we're going to show you today. Even the smallest library, 162 lines of code, can introduce flaws into your application. And there are a lot of small libraries in the JavaScript ecosystem. Most libraries aren't even directly included, but they're actually included by other libraries. In other words, one library will include another, which may include another, and that's something that developers often don't realize. We'll show you that more libraries doesn't always mean more problems. You can actually build an application with hundreds, sometimes thousands of libraries without introducing a ton of vulnerabilities. There are a lot better ways to prioritize fixes than by severity alone. So we'll show you a few different techniques that you can use to make sure that you're fixing what matters most. And then finally, we'll show you that 81% of patchable vulnerabilities can be fixed with a minor library update. And most updates are small, even when one update may introduce a new vulnerability, which then you have to patch again. It creates this chain. So we'll do some analysis of that as well. A little bit about us. My co-presenter, Ben, senior data scientist at Scientia, spent his whole career in data science. I'm chief research officer at Veracode, and I've spent my whole career in application security. And so that's why we think you should spend the 40 minutes listening to us today. All the data in this report comes from the Veracode State of Software Security, which is something that we release annually since 2010. We take all the customer data from the scans that we do for our customers, we anonymize it, and then we report on trends that we're seeing in application security. As that data set has gotten larger and larger, we have teamed up with the Scientia Institute, who is specifically good at doing data science on cybersecurity data. And so they've helped us with the last few editions of this. These reports give us and the readers insights into industry performance. It allows our customers to benchmark themselves against their peers, and it gives security practitioners and developers advice for improving AppSec. One other note is that this talk includes more than what's covered in the report. We did this update chain analysis, which was not in the report, so that's going to be tagged onto the end. Also, we've made a point to tag every chart or figure that we've used that was from the report so that you can cross-reference it back if you happen to go read the real report. You can grab the report on the Veracode website or on the Scientia website. So today's agenda, we'll go over the data sources for the study and some inherent biases. We'll talk about library usage, both direct and transitive. We'll talk about the flaws that we saw in those libraries and some of the patterns that we uncovered. Then we'll get into that funnel of fix prioritization. How do you get at that huge amount of fixing and patching to do in the most appropriate order? And then what do those update chains look like when one library patch introduces a new vulnerability? As far as I know, this is the largest known quantitative study of application security findings anywhere out there, and it has been since its inception. This particular report covers 12 months, and that includes 85,000 unique applications and 351,000 unique libraries. Any report based on data that comes from an automated testing tool is going to have certain biases in it, and so I want to acknowledge those. There are always going to be false positives. That's things that the tool finds that are not actually there. And there are always going to be false negatives, problems that are there that the tool is unable to detect. Then there's selection bias. As I mentioned, this data set is based on Veracode's customers. So anybody who's not a Veracode customer or who doesn't take application security seriously enough to be using a tool is obviously not included. Customers also choose which applications they want to analyze, so that gives a bias as well. Finally, there's an attribution bias, which is more of an interpretation. As you're reading the report, as you're watching this presentation, you may have the inclination to blame the outcomes that you see on things that may seem relevant but are not actually the reason why things happened. So another way of thinking about this is that we can tell you about what we see, but we can't always tell you why. We can speculate on that. So now that the disclaimers are out of the way, I'll hand it over to Ben to start diving into the data.
Thanks for that introduction, Chris. I'm really excited to be here. This is my first Black Hat briefing. And remarkably, I wish it could be under different circumstances, but I'm really excited to talk to you about the research we have today. So the first question we need to ask when we're thinking about library usage and the security implications of that is exactly how these libraries are being used in applications. And so the most basic question is just how many libraries get included in an application. So let's look at this first chart here. Along the horizontal axis, we have the number of libraries included in an application. Notice that it's on a log scale here. So equal distances apart here imply orders of magnitude gain rather than kind of a constant gain. And so we do this sometimes so we can have a better idea of widespread distributions when things get really disparate, a lot of variance. And then the dots here represent how many libraries get included in an application at various levels. So on the far left side, the blue dots, this is the 10th percentile. This means that about 10% of applications have less than that blue dot number for a specific language. And the right-hand side, the yellow dots, these are this is the top end, the 90th percentile. So about 10% of applications have more libraries than this. And the middle is the geometric mean. You can think about this like the median. It gives us a good idea of kind of the typical application, but it's robust to that big variance we see here. So there's a few things we want to point out. So first of all, there's just a large spread, a large difference among languages. So you have languages like JavaScript where it's typical to have hundreds of libraries included in an application. And on the upper end, sometimes thousands. I think the top end is something like a couple thousand libraries get included in a single application. Whereas other languages like Python, .NET, these have a couple dozen. And so this really illustrates kind of the philosophy and the culture that's built up around these languages. Whereas you have JavaScript and Ruby, which kind of have smaller libraries that have single functionality. So they're wrapping up a single function into a package that gets pulled in. Whereas these other languages are kind of more complete. You have families of functions together that get wrapped up in a library that get imported. So both of these have security implications. So with lots of small packages, you're potentially bringing in lots of code developed by lots of different people, increasing that risk surface. But even with the kind of more unified packages, you may be pulling in things that you don't need, functionality that exposes that risk surface potentially. So kind of both ends of these things, neither is better than the other, but they both have their security implications. Now, the obverse of this is how popular are some applications, how popular are some libraries. So how many applications use a specific library. So for this visual, along the horizontal axis, we have the percent of applications that are using any particular library, and the dots here are actually individual libraries. The color of the dots indicates kind of how dangerous they are, and Chris is going to go into this more a little bit later. But the dark blue indicates that there's no known flaws. The kind of gray blue there indicates we know there are some flaws. The light blue means there are flaws and there are proof of concept exploits for those flaws. And the yellow means we've actually seen those exploited in the wild. So again, we've broken it up by language here. JavaScript, the odd duck out here at the top again. We have libraries in JavaScript that are used in more than 90% of applications, which is just really remarkable that there are libraries out there that it's almost guaranteed that it will be included in an application. We're going to talk specifically about what those are because JavaScript is such a strange duck. And then as we kind of go down, we see things like .NET and Swift at the bottom there, where even the most popular libraries aren't even used in half, or in the case of Swift, like a third of applications. So there are no must-haves for those. But of course, JavaScript and Ruby in the middle, we have lots and lots of libraries that are used very, very commonly. And so kind of as an illustration, let's take a minute to talk about JavaScript. Because it is so weird, we really need to talk about it and get an idea. So on the right-hand side here, you have the top 10 libraries used in JavaScript. And notice that top one, inherits, used in 92.3% of applications. And even like the bottom of the top 10 is used in 83% of applications, almost 84%. So what we really want to do is kind of dive in and think about these and do a little bit of a case study. So as we know, JavaScript applications are incredibly small, incredibly numerous. I like to think about left pad. That was an incredibly small library. All it did was add characters to pad out a string in JavaScript. A developer pulled it off GitHub and broke like half of the internet. And so that's kind of the same thing we're seeing here. Really small libraries, particularly the top three, all have less than 1,000 lines of code each. And in fact, that top library inherits only has 36 lines. And what all that does is replicate some functionality that's in jQuery. And if it's not available from jQuery natively, it re-implements it. The other ones have less than 1,000 lines of code. Debug and MS, we're going to talk about them a little bit more in a second. IsArray, which makes this top 10 at 6, only has 4 functional lines of code and does exactly what you think. So again, these are getting pulled into applications really frequently. So that's not to say that even though they're really small, that they're not prone to flaws. In fact, the 2 and 3 libraries, Debug and MS, have versions that have known flaws with CVEs. They're both denial of service CVEs, and they're both, these are really popular libraries that get pulled in a lot. And they have flaws, even though they're only 790 and 162 lines, respectively. So it is certainly something that we need to think about, that even if you have small functionality that's wrapped up in a package, you could be increasing your risk surface by bringing it in. So when I've been talking about this so far as the popularity of libraries and libraries that come into applications, I've been glossing over a big thing, which is versioning. So on that previous slide, I'm treating all versions as the same. So if any version of IsArray gets included in an application, then we include it in that chart. But it's instructive to look at kind of the distribution of versions and see what developers are putting into their applications. So a few things that are just interesting here. Along the horizontal axis, we've got individual version types you can see labeled there. And the vertical axis is the number of libraries that have any particular version. Now, just one word of caution, I'm only showing libraries here that we managed to parse the version number is in. Developers do a great job of trying to conform to the semantic versioning system, but they don't always do it. You get weird things like 1.2 point revision 7, which is not actually a good semantic versioning number, but we're able to parse quite a few of them. Some interesting takeaways here. About 18% of libraries that get included in applications use a major version of 0. These are these pre-release versions. We think, maybe they are more prone to flaws, although we didn't see a lot of evidence of that. And so, developers are willing to take a risk if it's got the functionality they've got. The other thing that I just like about this is it's very regular. We've got these big spikes at major versions, this kind of exponential decay down to the next major version, and then another spike again. And those kind of blocks also decay as we go to the right. So there's more about this in the report. I encourage you to go look if you kind of want to dig out your own story. So when we're talking about including libraries into applications, there's really 2 ways that we can do that. It's either the developer can directly include it, or they can, or a library can get included because it was part of another library. As the saying goes, it's turtles all the way down. And this is pretty obvious, right? Libraries, like applications, aren't built in a vacuum. Developers are going to use those other libraries, that other functionality, and bring it in a way when they need it. So when a developer includes a library in an application, they're including every library that uses. And so we're going to talk about, there's 2 different types of dependencies. One are direct dependencies, where that developer just says, yes, import this. And the other ones are the transitive, where it resolves all those dependencies and brings all those into the application. So we wanted to look at different applications and see how they broke down on this kind of direct versus transitive line. So again, there's a lot of variation by language, so we broke it up by language to show that. On the top here, we've got .NET. Now, the blue bars represent applications that have more direct dependencies than transitive, and that means about 2/3 of the inclusions are, or 2/3 or more of the inclusions are direct. So about 90% of applications fall in this, for .NET, fall into this category, that almost everything is direct, where about only 9.3, which is more than 2/3 of the application libraries, are transitive dependencies, and then about 1% are balanced. And so we can see kind of as we go down and look at the different languages, there's again quite a bit of variation. So Swift has this big chunk there's a lot of balance, where we've got a lot of direct and transitive dependencies. And then kind of at the bottom, we've got Ruby and JavaScript, again, these web applications with smaller libraries, where it's mostly transitive dependencies. So when we saw those applications with 1,400 dependencies in JavaScript, it's likely that most of those were dependencies of libraries, not directly things that were pulled in by the developer. And so this is a lot of risk surface, a lot of flaws that might be included in an application that is not directly thought about by the developer. It's just pulled in automatically in your build system. So definitely something that we need to be cautious about. And then, so what's the implication for flaws here? So two flaws, and Chris is going to get to this directly after me, but as a baseline, about 70% of applications have a library with some sort of flaw in it on the first scan. And then if we look at kind of the breakdown of those flaws across the dependency type, more than a plurality, 46.6, are transitive dependencies. That is, most of the flaws that get included in an application are from these transitive dependencies, not direct inclusion of libraries. About 42% are direct inclusion, and then occasionally we have both. So somebody imports a library, but it's also included as a transitive dependency, and that has a flaw in it. And so this is, I think, a really important point, is that when you're developing your application and you're pulling in libraries, you don't just have to worry about the flaws of things you're directly including, but you have to worry about things that are pulled in by those library developers, those dependencies. And so it's really about managing that kind of fan out and those dependencies as it goes. So Chris is now going to dive into talking about the flaws, where they show up in different languages, and the types of flaws in different applications that we've seen.
Now that we understand the library ecosystem, let's take a look at the flaws that we inherit by using them. Here we're showing a scatter plot where we compare the number of libraries included in the application on the x-axis with the number of vulnerable libraries on the y-axis. One black dot represents one application. And when there are lots of them in the same spot, we use color to indicate the density or the count of applications. So the brighter the color, the more data points at that particular location. Also be aware as you're looking at this that both axes use a log scale. There's a few interesting notes here. For Java, JavaScript, and Python, we see a definite scaling relationship. The more libraries that are included in the application, the more of those have flaws. And this is the most obvious in the Python chart, where you see that concentration line, the green bright spot, trending with a clear path up and towards the right. So the more libraries you include, the more vulnerabilities you get. Ruby is kind of a mixed bag. You see dots all over the place, but you also see a small concentration of apps around the 100 libraries mark, where there's about 20 of those libraries that are vulnerable. There's a little bit of a blue area there. Now, Go, .NET, and PHP are interesting in the sense that most of the concentration is near the bottom of the chart, indicating a very small number of flaws, even as the number of libraries included increases. So this tells us one of two things. Either the library ecosystem itself is safer, or that developers in those languages are actually better at avoiding the bad libraries. More on that later. So what you should take away from this is that in nearly every language, there are applications with hundreds or even thousands of libraries that still have zero or very few flaws. And those are represented by the black dots sort of as close to the x-axis as possible. So it is possible to have those very large applications without introducing a ton of flaws. So that's nice to know. Here's a simpler view, but still broken down by language. And we think the data points shown in blue are the most interesting in illustrating the point that language selection has a real impact on open source risk. On the horizontal axis is the percent of libraries in that language that contain at least one flaw. On the vertical axis is the flaw density, or the average number of flaws per vulnerable library. Let's start with Go. Go has a high percentage of libraries with flaws, but an overall low number of flaws per individual library. Compared with Go, PHP has an even higher rate of flawed libraries and over double the density of flaws in a given library. So if you pick a PHP library at random, there's a better than 50% chance it contains a vulnerability. So going back to what we saw in the previous slide, it would actually appear that Go and PHP developers are pretty good at picking safer libraries despite these really bad odds. Swift and .NET are both very different ecosystems from the other languages, tied to a particular operating system and deployment style. Both of these languages have a low percentage of flawed libraries, and .NET does better than Swift on both metrics, despite a library population that's over 17 times bigger. Now, instead of language, let's look at the types of vulnerabilities that crop up most often. Most people are familiar with the OWASP top 10. 3 of those categories in the OWASP top 10, shown in blue, account for nearly 3/4 of all the vulnerabilities. Cross-site scripting is probably not a surprise. It's been around forever. It's fairly prevalent. But the others may be a surprise. For example, A8, insecure deserialization, is number 2. And when we looked at first-party code, deserialization came in 8th place. But here for third-party is 2nd. I'd also expected injection to be a lot higher, but it shows up only 8.8%, which is less than half of what we see for broken access control. So it's not exactly what we expected it to be. Now, if we take all this data and we break it down by both language and flaw category, we can actually see where the hotspots are. I put a star by the categories that were in the top 3 on the previous slide. So to read this chart, take any row and column, say A1 and PHP. And that tells you that 18.6% of PHP libraries bring along with them at least one injection vulnerability. The darker the cell, the worse the situation. If we look at broken access control and cross-site scripting, A5 and A7, we can see they're not only top 3 overall, but they're in the top 3 regardless of language. But looking at the bottom row, insecure deserialization is heavily weighted towards Java and PHP. And we expect to see a lot of it in Java because the first really modern talk that brought attention to this category covered 0 days and gadget chains in Java. This was a few years ago. Apache Commons, Spring, Groovy, some of those. But apparently PHP has a lot of it too. So insecure deserialization ended up at number 2 overall, almost entirely because of the volume from Java and PHP. If you look vertically, PHP just seems to be full of bugs, no matter which category you look at. So it's easy to look at this data and be overwhelmed with the sheer amount of vulnerable code that we inherit simply by developing software the same way that everybody else does, by borrowing functionality. So in this section, we'll look at some ways to prioritize what's most important to fix. There are a few different ways that we can take this huge list of vulnerabilities and filter it down. You can think of it like a funnel. Everything goes in the top, and then what we care about most comes out the bottom. So the first filter is pretty easy to understand. Not all vulnerabilities have exploits. Vulnerability reports contain a pretty wide variety of information. Sometimes a researcher will publish a very detailed advisory with information on how to reproduce the vulnerability or how to exploit it. Other times, a library maintainer will roll the fix into a release that doesn't really give much information about how the attacks might work. Most people don't have the skill to develop an exploit, but there are websites that crowdsource proof-of-concept exploits for known vulnerabilities. ExploitDB is one of them, and then there's some commercial products like Metasploit and Canvas that provide weaponized exploits, which are essentially just more reliable versions of proof-of-concept exploits. So we use some data from Kenna Security that cross-reference known vulnerabilities with publicly available exploits, which gives us a first cut as to which vulnerabilities are more likely to be exploited. So on average, the blue vertical line, 20.7% of all vulnerable libraries have a proof-of-concept exploit. But as you can see, it varies widely by language. And once again, PHP is that unfortunate leader. And when you look at exploit availability by OWASP top 10, the outliers in the chart are the same 3 categories that we saw before. So not only are they more prevalent, they're more likely to be exploited, especially A8 and A5. Now you see that cross-site scripting is a little bit further down, only less than 10% of available exploits. But oftentimes cross-site scripting is so easy to exploit that you don't need to release a tool. So I would suspect that that number in reality is a little bit underreported and probably a little bit higher. In general, a skilled attacker can create an exploit for most of these, so treat any of these numbers as minimums. But still, using this chart, combined with the previous one, you'd probably prioritize patching for a PHP deserialization bug before a Python injection bug, right? Even though they might still have the same high CVSS score, high impact, one represents more risk to the application than the other because of that presence of an exploit. Now, prioritizing the vulnerabilities that have a public proof of concept exploit gets us from 97.4% of applications down to 52.3%. That's pretty good, but there's more. Let's look at a couple other factors you can use to prioritize even further. Canis Security provided us some additional data that tells us which vulnerabilities are being actively exploited in the wild. Now, they do this by collecting telemetry data from various network security vendors to demonstrate that. Now, obviously, it's impossible for any of these tools to detect every attack. The accuracy is dependent on having good IOCs, but it's still something we can use. So if you apply that filter, now you're down to only 25% of applications. Finally, we can look at how the application actually uses the vulnerable library. Libraries have a lot of code in them, aside from those tiny JavaScript ones. In plenty of cases, an application may be dependent on a vulnerable library, but not actually executing any of the vulnerable code. So for example, let's say I download a math library because I want to use the square root function. And it's a vulnerable library, but the vulnerability is in the Fourier transform function, which is something that I never call. So even though I'm using the library, it's impossible for an attacker to trigger that vulnerability because I don't use that function. So the Veracode product where this data comes from looks for an execution path. And if it sees one with a high degree of confidence, it flags it to say this application is definitely using the vulnerable library function. So if we use this as our final filter, that gets us down to 1% of applications. And this is not to say we should ignore all the other library flaws. None of these filters are perfect. There's false negatives at every stage, but this gives a framework for prioritizing what's most likely to be exploited and what's most important to fix. One more piece of good news is that most fixes are minor. If you've ever been a developer, you know that a library upgrade can have side effects. Upgrading to a new major version can have a blast radius where stuff breaks unexpectedly. So for example, an API or a config setting might be deprecated, and so that would break other code that you're using that depends on those deprecated things. A minor version or patch is usually safe though. So of the 73.8% of libraries that do have an update available, the vast majority of them, 81%, are a minor version or less, minor patch or revision. Meaning there's a really good chance you're going to be able to apply that update without breaking anything. So let's say you're using a vulnerable library and you patch it. That's great. But oh no, now you find out the new version has a different vulnerability, so you have to patch again to get rid of that one. This could go on forever and ever, right? Well, maybe not. We wanted to figure this out because otherwise you just have to, you're in this never-ending cycle. So Ben did some extra analysis on these scenarios to understand what these update chains actually look like. And so I'll hand it back over to him to talk about what he's found.
Okay, so as Chris said, things are never that easy. So we really need to look at what these update chains look like. So when you go to update a library, what's the next step? And so before we kind of dig into the statistics and dig into the data and see what it's like, it's instructive to think about it ahead of time and think about what possibilities there are. So let's start with the good possibilities. And there's two. The best would be there's a single update to a known version, to a version with no known flaw. That is, we just kind of move to the next version and it's fantastic. The next thing that's maybe less ideal but still good is if we can do multiple updates and get to a version with no known flaw. So you can update your library a couple times. Maybe you have to step through like major or minor versions, but you do get to that version with no known flaw. Now, the less ideal version is that there's no update available at the end of that chain. And that can either be immediately there's no update available, or after multiple steps there's no update available. Now, this isn't exactly the worst thing in the world because if an update is available, it may update a portion of the library that was flawed that you're using, and new flaws that get introduced don't necessarily affect your application. They're not on that execution path, or they're in a portion of the application that's never exposed in a way or that you can control in a different way. Now, there is one last possibility that we actually didn't think about ahead of time, but found in the data, is that the suggested updates are circular. So occasionally we'll have a library version update, another version update, and then we'll get to an endpoint and it'll say, no, if you want to avoid this new flaw, you should downgrade to a previous version. And so when this happens, it's not ideal. So you kind of have to pick your poison and where in this circle it might be that your flaw is. Now that's fine. So we wanted to look at these all possibilities and see what it looks like, and then ask some questions about what these chains are. So first of all is just what is the proportion of those possibilities? Where do these end? How many steps occur in that change? And are they going to significantly increase that update size? So where we said we had mostly patch and minor versions, are we going to have to now move to mostly major versions if we check out the chains? And thankfully, I mostly have good news for you. So how do the chains end? About a little over 2/3 end in this version that we has no known flaw. So about 34% get to that multiple steps to a version that's unflawed, and then about 33% it's just a single step. So that's good. We can still do that. The 26.2, that's what you saw before. These are libraries that have no one-step update. And then about 6.4, you might have this multiple steps and kind of get stuck and there's nothing to go to. Now, blessedly, these circular updates are rare, only about 0.5% of the time. So you may have to kind of pick the least worst option in those update chains as you go. So that's good news for us. The next question, how long are these chains? Most are relatively short. So across the horizontal axis here, we've got the update chain length. We just looked at all those lengths. And we can see that most are length 1. The colors here is whether the final version has flaws or not. The blue is no flaws. The yellow has flaws. And in fact, 90% of the chains that end in a version that doesn't have a flaw actually are less than or equal to 4 steps. So you're only going to have to do 3 updates before you get to that end chain, 3 little jumps. Now, interestingly enough, occasionally we get these really long ones, like 33 updates to the final version. But again, those are blessedly rare. And because that ends in a version that still has a known flaw, you may be able to pick something else along the way that has a flaw that's more amenable to your application and is a little safer. So it's about managing kind of what those flaw types are. Now, as we've seen over and over again, these things vary by language. And so .NET tends to have these really long update chains. And in fact, on average, has about 7 steps before you get to an unflawed version or the end of the chain. On the other end is Go, which only has averages about 1 step. Interestingly here, this is the one place JavaScript is in the middle of the pack, which is about 4 steps before you get to the end of the chain. So as always, the language choice makes a big difference. So this is the last visual I'm going to show you, and there's a lot going on here. So we're just going to take a minute to kind of parse it a little bit, and it's actually easier to look at than you think it is. So what this is really kind of a bar chart that shows how the different proportions change across each bar. So on the left-hand side, we have kind of the type of updates we have. So we can either have those one-step chains, the multi-step chains that end in a nice clean version, that can end in a flawed version, or there's no update available. That's that yellow chunk at the top. And then in the middle, we can see this the 73.4% of flaws, that's the height of the bar, that have any kind of update available. Just one step and we can get to something that's different, has a different type of flaw that you might be able to accept. And what we've done is we've colored this by the size of the update. So that blue at the bottom is the patch, the kind of gray in the middle is the minor version, and that lighter gray at the top is the major version. And so these are the proportions that we saw in the previous chart that Chris showed. And what we can see is how those flow from left to right, and how those change as we go through these chain updates. So in the far right version, it shows how those proportions have kind of changed for major, minor, and patch versions. And so what we see here is where we had mostly patch versions on that single update to fix the flaw. On the right-hand side, we have mostly minor versions. So that blue that goes across to the minor version, it shows about a third of them that were patch updates on that first step end up being minor version updates in the chain step. Interestingly, like most of the patch stays the same, and we see most of the minor versions stay minor versions. A few go up to major version updates, and then about 10% of those go and don't actually have an update at the end of the chain. So that's what those kind of different flows show. So this is like a good outcome again. About 2/3 of our flaws have that good ending, and still most of those, about 75%, are small updates, minor versions or less. And so we're in good shape. Even though we know that you can do multiple updates, we're still going to end up with a clean version most of the time that's going to be a small update. So that's the last visual I have. I'm just going to end with a few takeaways, and then we can get to some questions that I will answer in a month and a half when I present this on a webinar. So the first takeaway is open source software has a surprising and surprisingly variable number of types and quantity of software flaws. I don't think it would come to a surprise from anybody that yes, open source software is flawed, but the extent and the types and the changes were something that's really interesting, and pulling those apart and understanding how those interact with applications and their use, I think led to some surprising results. I think this idea that most of the flaws that come from transitive dependencies is really important to understand. So when you're writing an application, you're pulling in all that data, you have to understand or pulling in all those libraries, you have to understand it's not just the libraries you're directly including, it's everything that those library developers used, and those library developers used, and those library developers used. So you potentially have to manage, hundreds of developers when you pull in one library. And really, it is about management. It's not just it's about management and prioritization. It's not just fix everything, update everything. It's about fixing the stuff that's important, things that have that proof of concept, things that have that exploit in the wild, things that can be fixed with just a minor update. Those are easy things to do, and not necessarily, they don't mean a huge refactor of the code. And then, of course, language selection does make a difference. Developers don't always have the luxury of picking the language ahead of time, but sometimes they do. And if you're worried about security in your application and know kind of what the application you're building is, some of this can give you guidance on what language you might want to select versus shy away from. And so I think these are all just kind of interesting lessons that we can take away. And there's lots of interesting questions that get brought up in this research, and we're looking forward to working on that in the future. But until then, I'm excited to hear about your questions. Thanks for making my first briefing a memorable one. And let's talk a little bit.